Okay, example 2 for the one-sided limit strategy. So we got the limit as x approaches 3 of x squared minus x minus 6 all over the absolute value of x minus 3. So let's first take this x minus 3, this absolute value of x minus 3, and let's turn it into a piecewise function. First off, notice that we can't directly substitute 3 into this limit because the denominator will equal 0. So we got to do some more algebra here. So remember, the absolute value, basically everything has to be positive. So if there's a negative inside, then we'll change that negative into a positive number. If it's a positive number inside, then we just leave it as that. So this x minus 3, if x minus 3 is positive, then we just leave it as x minus 3. So that's if x minus 3 is greater than 0, or if x is greater than 3. We just brought the 3 over. Now, if x minus 3 is negative, then we have to multiply it by negative 1 to make it positive. And that's when x minus 3 is less than 0, or when x is less than 3. So we got these two restrictions here, and the absolute value equals different things on these restrictions. So let's now let's make an expression, a piecewise expression like this for this whole function. So let's rewrite it. Let's split these two functions up. So we'll have x squared minus x minus 6 over the absolute value of x minus 3. Now notice how we can factor this x squared minus x minus 6. That will just equal x minus 3 and x plus 2 all over the absolute value of x minus 3. And changing it to a piecewise function, so when x minus 3 is positive, or when x is greater than 3, then the absolute value of x minus 3 will just be x minus 3. So we can rewrite this as x minus 3. We'll rewrite the numerator, x plus 2 over x minus 3. And that's when x is greater than 3. And when x is less than 3, the absolute value of x minus 3 is negative x minus 3, because we'll have to multiply that negative number by negative 1 to make it positive. So let's rewrite the numerator here. So x minus 3, x plus 2, and then this absolute value is going to be negative x minus 3 when x is less than 3. And then we could simplify this even more. Notice how the x minus 3's here will cancel out, so we'll just have x plus 2, and that will be when x is greater than 3. Or, notice how the x minus 3's cancel out here, and we'll be left with negative x plus 2, and that's when x is less than 3. So we took our original function, and we made it into a simplified piecewise function. So let's take this piecewise function and let's graph it. Now, as in example 1, it's not the y values aren't they're not just constants. So this one won't be as easy to graph. So we'll probably have to make a table of values. So let's start with the most left piece. So this is when So when x is less than 3, let's make a table of values. X and the y value will be negative x plus 2. So we could have 3, and then when x is less than 3, so let's pick 2, 1, and 0. So when x is 3 and we plug it in here, we'll end up with negative 5. If x is 2, we'll have negative 4. negative 3, and if we plug in 0, we'll have negative 2. Now let's deal with the right piece. So this is when x is greater than 3. If we make a table here, we'll have x, and the y value will just be x plus 2. This is for when x is greater than 3. So we'll have 3, 4, 5, 6. So plugging these x values into this expression for y, we'll get 5, 6, 7, 8. Alright, so now we have a table for both pieces of this piecewise function, so we can, let's graph it. So the point at which they're separated at is at 3. So let's graph this portion here first. So we'll have 2, 1, and 0, and when x is 3, the y value is going to be negative 5. So notice how the y value for 3 on the left piece is negative 5, but it's not defined at 3, right? So we put a hole there. At 2, we'll have a y value of negative 4. At 1, we'll have negative 3. At 0, we'll have negative 2. And so it's just a line that will just keep going like this. Now this is not necessarily to scale, but you get the gist of it. It's just a line of negative bracket x plus 2 when x is less than 3. So now let's work with the right piece. So when x is greater than 3. So when x is greater than 3, we have a y value of 5. But notice how it's not defined at 3. So there will be a hole here as well. And then 4, 5, 6. So at 4 we have a y value of 6. At 5 we got a y value of 7. And at 6 we got a y value of 8. So this is a line that just keeps going like this. Let me just erase this line here so there's no confusion. Alright, so that's how this piecewise function is going to look on the graph here. We just plotted the points that we had in the tables. And now we can take the limits, right? So the limit as x approaches 3 from the negative side of f of x being this whole function here, which is equal to this piecewise function, which we simplified, which is this graph. And as x approaches 3 from the negative side, the y value approaches negative 5. And then the limit as x approaches 3 from the positive side of f of x. So if we look at the graph, as x approaches 3 from the positive side, it's equal to positive 5. And because the limit is approaching two different values from both sides, we can conclude that the limit as x approaches 3, the general limit, does not exist. So that's our answer for this. This limit doesn't exist. So let's go over a recap of what we did here. So we took this, first we took this absolute value of x minus 3 in the denominator, and we made it into a piecewise function. And then we made a piecewise function for the whole function using what we found here for the absolute value. So we took this function and we simplified it to a piecewise function of this. Then we took these two pieces, we made tables for when x is less than 3, for when x is greater than 3. Then we plotted the function, and then we took the limits from both sides. They were different values, so the limit doesn't exist.